Angular momentum for a system of particles. The angular momentum of a system of particles about a given point is equal to the vector sum of angular momenta of individual particles. We have deduced that the angular momentum, deduce the expression for the angular momentum for a single particle, that is L. L is equal to R cross P. But if you have a system of particles, then the angular momentum for a system of particles L, this will be the capital L, that is equal to the vector sum of the angular momenta of individual particles. So L will be equal to summed over Li, I from 1 to n. And the angular momentum of the ith particle, if you define the angular momentum for the ith particle, then you will write like this: Li will be equal to Ri cross Pi, where Ri is the position vector of the ith particle with respect to the given origin, and Pi, which is equal to Mi Vi, is equal to the linear momentum of the particle, that is ith particle. So you can write the angular momentum L is equal to summed over all Li, that is equal to summed over Ri cross Pi. Ri you can write here the vector. So this is a generalization of the definition of angular momentum for a single particle to a system of particles. For a single particle you define Li is equal to Ri cross Pi, but for a system of particles the angular momentum is equal to summed over all Li, that is summed over Ri cross Pi. In linear motion we write Newton's second law as F external is equal to dp by dt for a system of particles. But what will be the rotational analog of this equation? F external is equal to dp by dt, that is the Newton's second law. Total angular momentum of a system of particles we have defined L equal to summed over all Li, and differentiating both the sides with respect to time, we get first derivative of the total angular momentum is equal to first derivative of all Li, and that is equal to summed over I first derivative of Li with respect to t. And we have defined this is nothing but tau I. So summed over all tau I, and summed over all tau I, or we may write tau, that is equal to the sum of external torque and internal torque, where the external torque you may define summed over Ri Fi external, and for the internal torque we define tau internal, that is equal to summed over Ri cross Fi internal. And you should remember that Fi internal, that is equal to 0, because force due to the action and reaction pair of forces is 0. We have defined it, we have discussed it in the previous video, that is the force due to the internal force due to the molecules or atoms, since it acts in pairs. So applying Newton's third law, this will be equal to 0. So the total torque will be equal to the torque due to the external force. So define the first derivative of the total angular momentum is equal to the torque due to the external force, that is the external torque, that is the time rate of the total angular momentum of a system of particles about a point is equal to the sum of the external torques acting on the system taken about the same point. And this equation tau external is equal to dl by dt, this is rotational analog of the equation F external dp by dt. This equation we basically use in linear motion for a system of particles, and for rotational motion instead of force we take torque, and instead of linear momentum we take the angular momentum. And this is for Newton's law for the translational motion for a system of particles, and this is for rotational motion.